Gadget UK here again, back for another build video, something that I'm going to create myself, and it's in no small part due to the work by Mattias Heinrichs. So I'm going to mention Mattias a number of times throughout this video series, maybe, because I've got a lot of footage. You'll remember the year before last, I think it was, when I did the AGA Multifix, just after I moved into this environment here on this bench, actually. In that video, I threw a comment in there. I'm surprised no one's actually ported this to a replacement Amber. Old TVs couldn't do that kind of resolution, so they had to be interlaced, so it would show the odd scan lines, 200 of them, and then the even ones, 200 of them. And you'd have a couple of frames of data, as far as I can understand. You know, the odd scan lines, the even scan lines, and they would alternate between what is displayed there for, you know, every other, you know, full screen of display, if you like. And the flickering is because, you know, the lines are overlapping with each other. You see one frame, then the other, then the first one, then the other one, etc. Can be written to as the pixel data is fed from Amber. And at some point, I may try to produce in CPLD my own replacement of Amber, actually. I wouldn't mind having a go at that. I've talked about that a little bit in Discord. It's I can't imagine it being that difficult to achieve. The hardest bit is producing a proto board with a CPLD on it and wiring everything up so that all of the connections are in the right places effectively. Actually trying to get it to go into a PLCC socket is the biggest challenge, I would say. But the complexity here is, if you look at you know, the line RAM actually on the right hand side, you know, you've got RST, RSTW, read and write signals there. It's getting the timing of both of those, you know, on the line RAM, and similarly on the frame RAM, all synchronized in such a way that the pixel data goes to the right chip at the right time. That's the complexity in this, you know. And I guess it may have been quite complex back in the day, and I'm not suggesting it's easy, but that's all Amber's doing. That really is all Amber's doing. There might be a bit of complexity when you start to look at some of the oddball resolutions in the Amiga. That might be where things get complicated. So yeah, anyway, I might have a go at that at some point in the future. I'm surprised no one's done it already, to be honest, but I mean, you've got things like the AGA Multifix, so you could argue it has been done because the code there, and in fact that's a good starting point for a project like that if you wanted to have a go yourself, and that's probably what I would do. The Amber being the scan doubling IC that you get on an Amiga 3000. You also have it on the GBA 1000. And I also mentioned it in the GBA 1000. I specifically put turn pin socket in place instead of a PLCC socket. You know, this is PLCC, the Amber chip. And I put turn pins, so in order that I could put the socket in there. Hence this has, you know, got a heatsink and a socket there. It goes into my GBA 1000. Right, I want to get Amber on there, but in a way that allows me to create a prototype for Amber. And at the point when I did that in the video, I explained the reason I did that is so that I could prototype it. And at that point, I hadn't completed a PCB design. I've omitted showing you the actual design of the PCB, but I'm going to talk about it as we build the first prototype, and this ends up being a couple of different board revisions. The inspiration for this obviously hasn't just come from Mattias Heinrichs, it's come from Stephen Leary, from Live 2, from Mike T, from Retro HQ, from Terra Onion. All of the companies that have, and people that have interacted with me on my channel, sent me CPLD based products, FPGA based products, replacement chips, you know, multi-carts that use CPLDs and FPGAs and all this wonderful things, really. So a lot of inspiration from all those guys that have interacted with the channel over the years. I can't thank you all enough. So there's the inspiration, and obviously that throwaway comment that I made when I analysed the AGA Multifix and went, I can see how this could fit into an Amber. Yeah, I'm sure it'll be easy. Well, yeah, there's some challenges, as you'll see. If you want to know more about PCB design using KiCad, look back at the video I did on the 27C4096 EEPROM adapter, because I talked about it there, and I think I talked about it on a previous video as well. I'll stick a link top right, I can't honestly remember, and a link down below. KiCad is really easy. You just, you know, literally just, you know, set your grid size so that you're snapping to the relevant points, shape your board to the right physical size, choose your little components and plop them down, and then just draw traces, route them on the top and the bottom side. It's really easy stuff, KiCad. When you use it the way I do, Fisher-Price mode is what I do with KiCad. But again, we'll talk about that more through this video series. So as I was designing the PCB, I tried a number of different things, and you can see here I was using free routing. After I actually laid out my schematic in KiCad, I tried to use a free routing plugin, and you can see it going round and round and round, where it tries to use, its intelligence, its algorithm to calculate the possible routes for all the connections. There's a problem with that, and I've talked about that in the 2704096 EEPROM video. It's all about when you lay your chips down on the schematic, when you've got a CPLD as one of those chips and it's got hundreds of I/O pins, and you don't really know what the optimum position to route a given I/O pin would be to a PLCC socket like this. Therein lies the problem, is that you don't get ideal routing, either manual or automatic. So what I mean is, an I/O pin here, when the CPLD is in place, you want the I/O pin to be right next to it, so that you've got minimum routing. If on the schematic you've laid out, and you've got your two different chips on the schematic, and I covered this in that other video, if you join that pin to the I/O pin that's most logically next to it, that can end up being up here, which means it goes through a via, and then the next one goes through a via, the next one goes through three vias, and then you've got one going for four vias, three vias all over the place. Really bad routing is terrible. Auto routing is not a good thing to do with something like that, and auto routing is people frown upon anyway, so I did it manually. The process of actually routing the board, when I first started off, that's the approach I took, of doing the schematic first, and I had no end of trauma. I tried the routing, that wasn't working, the auto routing, that wasn't working, and I thought, I need to do this manually. So then I scrapped the schematic and just left my two chips there with the pinouts around them, but no connectivity between them, and then went over to KiCad and manually started drawing traces according to how I felt it was best to position the CPLD on there. There's obviously a number of things that go into a design like this in terms of thinking about all of the implications, all of the pins that are around it. You have to look at every single pin, and then you have to consider, will the CPLD have enough pins, I/O pins, to do the job? Is it going to be fast enough to do the job? Well, the same family of chips have been used on the AGA Multifix and on other Amiga things, so there's no issues there. You also have to think about current implications. You need to think about connectivity, what this connects to. The first obvious thing, I'll just try and move this over there without revealing it, is the hybrid, the DAC. The DAC is a difference. On the AGA Multifix, you've got a custom parts, a DAC that Mattias, spec'd up and fitted on there to do the job of something like the hybrid. And what's the issue in this design? 3.3 logic levels. On his design, he may have had a DAC that, or some circuitry in between that compensated for that, and the DAC could output at the correct logic levels but be fed with 3.3. Maybe you didn't. Maybe you just buffered it that way and it works okay. There's a bit of evidence of that, as you'll see in this series here, that when we come to, my first thought with it was, the logic levels aren't going to be sufficient for the DAC. We've got 3.3 levels, we need 5. And in the AGA Multifix, when we had that issue, I put a 74F245, I think it was, or 244 it might have been, on the 2000 to fix a problem with the 2000 HCT chips. And when we put an F1 on there, there's a difference between an F and a HCT in terms of your output logic levels. It was slightly lower. So on the screen, and I showed you that, I'll overlay it here, on the screen we saw dark RGB as a result of changing to that F chip. On the DAC that was coming out of the AGA Multifix, we saw the correct levels because it was being, it was being buffered correctly. In that case there, changing to an F series on the 2000 motherboard meant the logic levels were not quite as high for the hybrid. So the resistor ladder that has your 4 colour bits, if you think about it, it was slightly lower, which meant your overall brightness was lower. It seemed a bit darker. So that's a thought I have right from the start, trying to fit some buffers onto, here's a sneak peek of a PCB, onto a PCB that small. Good luck with that. That's impossible, I think, unless you widened it somehow. And I want to try and retain a similar size to the original Amber chip here to fit into this footprint. So it's a scan doubling IC. We're going to replace it with a CPLD. No one's done this before for Amber, so it's one of the customs that hopefully should get replicated in a way that allows people to build 3000s themselves, because you can now get, and there'll be more about this in this 3000 board here, there'll be a series on this. We've got a new SD-Mac in there to replace, you know, the original custom SD-Mac, which sell for £400 upwards, those, and you can now replace that. Yeah, Mattias Heinrichs is working on Ramsey replacement. I think someone might be working on the Super Gary replacement. The bottom line is, in a year or so from now, people will be able to build these 3000s just from a donor 500 or something, and, you know, a few bits from here and there, and buy your customs, you know, that are modern CPLD FPGA replacements like what I intend here, and you've got a 3000, which will just be absolutely incredible. And of course, if you've got a faulty Amber, you'll be able to replace it. And if you've got a GBA 1000, there must be hundreds of GBA 1000s out there with no Amber. Yeah, you can fit an Amber. So yeah, just picking up here, the first PCBs have arrived, and I'm going to talk about some of the issues as we go through this. You know, you'll get an idea of how I've designed this. Right, my prototypes have arrived for this Amber replacement, which I have named Marine. I'll talk more about that later. So I've got the JTAG connections at the top here. Obviously I need to now check everything here to make sure that my design has translated to a real PCB correctly, and that I've not missed anything. I think one of the first things I'm going to do, other than just having a bit of an inspection under the microscope here, is fit the 3.3 volt regulator. Yeah, there's some questionable things on this. Like, I stitched the ground here, and then on the underside a pad here, just to help try and dissipate heat. Bear in mind, that's not ground, that's VCC. It's, well, let's say VCC, 3.3 volts. Yeah, it's isolated from the ground around here, so I need to make sure I've got no shorts. But I did that just try and sink a little bit of heat there. The specs of, you know, the chip that goes here, obviously the amount of current it draws depends on the I/O pins that are used and how they're used, etc. There are formulas you can use on the actual data sheet to work that out, but I'm going off the fact that similar regulators have been used with this chip to do similar kind of things on other cards. Like Terrible Fire's used these chips, and he's used 3.3 volt regulators. All these use beefier ones, certainly for the 04060 cards, and potentially the 0301s. I'm not honestly, I can't honestly remember what was used on those, but I think a standard AMS 1117 was used on one or two of them with this chip. But as I say, it depends on how you use the chip, depends on how much current it draws, if that makes sense. It's obvious, you've got a load of I/O pins. If you're going to use all the I/O on there, and it's going to be used very high frequency, you know, even frequency is not the thing. It's about how much current each pin uses, etc. at any given point. But anyway, I think that should be alright. So I'll probably fit the regulator on here as one of the first things, fit my capacitors, fit the capacitors on the underside as well. Yeah, that one is tiny little thing. I hope I've got some of those. I'm sure I can reclaim one off another board. It's just 100 nanofarad to go there, and then maybe a 1 or a 10 or a 22 or something there. Same on this side. I've not really spec'd these up. Forget now, one of these is on the input, one of them's on the output, I think. So I may just fit a 1 or a 10 on each side here. You need to think about the size of those things though. They need to be smaller on the output. Regulator fitted, caps fitted, and then I think I need to maybe, well, check for shorts between the 5 volt and ground first of all. Check between 3.3 volts and ground. The 3.3 volt rail comes out this via here. Slightly thicker trace compared to these other rails, and it comes all the way up here. So check we don't have a short there. I mean, I can do that now on the multimeter. And then connect some wires up for the 5 volts and ground, which, you know, are going to be, you know, the grounds, for example. I can't really see because of the light. Yeah, we've got a couple of grounds somewhere up here, and there's a VCC somewhere. I think it's on the right side. I can't honestly remember where it goes now. It might be this one here. Yeah, I think it's that one, because I think it goes ground, output, input. So that's the 5 volts. It's going to be that pin there. And power it, measure 3.3. Do we have 3.3? And then check the 3.3 according to pin 1 here on the CPLD. And make sure we got our 3.3 in the relevant places, and check we've got ground in the relevant places around there. I think once I get to that point, I think what I probably need to do then is go around this and do a short test between the 3.3 and every pin on the outer connections, and do the same on the ground, and just make sure I've only got grounds. Maybe do the VCC from here and test all the way around, just to make sure that none of these other pins are going to ground, VCC or VCC 3.3, unless they're supposed to go there. Well, VCC 3.3 definitely not, but do you see what I mean? And then once I've done that, then I think we get the CPLD on and a pin header here, and we go and see if we can actually identify the chip. Yeah, if that works, I think what I'll probably do then is plug it into the GBA 1000, because I've got the socket, ready for this. Yeah, put the pins in here, fit it in, and just power it, and make sure we've got 3.3, and have a bit of a sense check around things, and make sure the machine works without any firmware on this. Shouldn't cause any issues, I don't think, not being flashed. And then from there I can then start to program it, work how to code it, etc. So I'm doing the grounds here, so I've got a ground there, and I've gone around every other pin on the profile here of the what would be the PLCC. So all the way around the board we've only got joins to there and there from that ground, so those 3 pins are joined together. And then up here we should have one of these joined to ground. I can't remember which one it is, it might be the end one, the left one from memory. Yeah, there we go. So we've got grounds to the PLCC, and if we check down here, I think pin 1 is ground, nothing 3.3, nothing to the 5 volts in. So those 3 grounds are right. I'll check that in a minute just to make sure on the schematics, according to the original Amber chip, that those are supposed to be grounds. And looking on the phone here, it's 52, 66 and 68 are generally always joined to ground. Bear in mind 2 of them are test pins, one's a test pin, one's a mem cell, but they're just always fixed to ground, so I'm just replicating that. Even though we could have done something more fancy with this, it's handy to have those 3 grounds, because we know on the board they're going to go to ground. Does that make sense? It seems silly to have only 3 grounds on there, but well, no, there are. Now, this is the next problem, is trying to work out the pin out on that. So like one's here, and does it go? I think it goes that way around, doesn't it? Or does it go that way around? I was trying to use my finger then to touch screen scroll that. Yeah, that's not going to work. Yeah, it's got to be that way around. So 68 it makes sense to me. I think it's a 68 pin socket. So 68 is going to be one of these. See, I think it's going to go 68, 67, 66. So 68 and 66, that would make sense, wouldn't it? It's a 68 pin socket. I forget where it is now. What's the ground down here? I've lost it. It's that one. Yeah, so I think it's like 68. Well, it's the 1, 2, 3, 4, blah blah. 68, 67, 66, 65, 52. That must be 52, I think. Is that right? I'll just have a look at the diagram again. Assuming I got the pin ordering right when I went counting around the corner there, because you know what, it's hard counting around corners on those chips. 52, where's 52 on here? Yeah, 52 is the ground. So you know what, I think I've got the grounds right. So the next thing is the VCCs, which I'm struggling to find on the diagram now. Hang on. And it's a similar thing where there's very few VCCs. We've got 18, 54 and 50. 18, 54 and 50. So that's 52. Let's just test that again. To those ones. Yeah, that's 52. So it must be 51, 50. That must be the VCC. Yeah, and it is. It comes down to the end pin here. That's right, 5 volts. So I'll do a similar thing with this now. First thing I'll do is just check what pins go to the 5 volts. It does take some time. You've got to be thorough and meticulous if you want to avoid burning out things. And well, get this right. If it needs to be revised, it needs to be revised. If I've missed something, I mean, I might be able to revise the board with a little mod if I have missed something simple. But if I've... Now that's a worry. What's that? I can't see where that goes. It goes... Oh yeah, that's the output. So we know we've got a pin over here. There, it's an easy one to find, so just remember that. We'll check that in a minute according to the pinout on the 3000 schematics. Should be 3 of these, shouldn't there? We found 2. We've got 2 connections so far. Guessing one's going to be up here somewhere. That's there, look. Yeah, I remember this now. It's like the ground's in the middle and you've got VCC on either end, and the other one's over here. So that's really easy to check those VCCs. And anyway, we've gone all the way around. So we know that that's... hang on, where's that gone now? That was 52, wasn't it? 53, 54. So if that's 52, 51, 50. So it must be 50, 51, 52, 53, 50 and 54. Let me just check the diagram again. Again, I'm assuming I'm counting the right way. You may find the one you count. Yeah, 50 and 54, that's right. So those are the 2 VCCs, 50 and 54. Hang on, it's those 2. Yeah. And then the other one is 18. So, yeah, we've got to hope that's 18. 1, 2, 3, 4, 5, 17, 18. Assuming I counted that right. So I think my VCCs are right. And again, if we just test from down here, nothing to those 2. So we've got no shorts between 5 volt and ground. It looks like we've got our 5 volts and grounds going to the PLCC part correctly. The next thing is test from the output here to this. Now I'm just going to make sure I do have a connection. There we go, somewhere we do. So we've got 3.3 volt going to the CPLD, but the key for sanity here is we shouldn't have any connections to our original amber socket. We should have a join here for 3.3. Yeah, that's right, 3.3 was on the end, I remember that. Let's just test the other ones. Yeah, so we've got ground, 3.3 on the JTAG connection, and then TDMS, TDI, TDO, TCK in between. Well, so far, this is looking good in that I haven't absolutely balked the design here, feeding power and ground to stupid places. I'm also not discounting the chance that I might need to alter the pinout on the CPLD. We've done this side, I know. I'm just, for my own sanity, just going along here, just to make sure I haven't missed anything. Stop at this end here, because I couldn't remember how far along here we started. But anyway, so that's that. Yeah, so I might need to reroute some of the I/O pins. I don't know, because there are special I/O pins that are better at handling clocks, and I think I fed heatsink to one of those, and maybe the 28 and the 14 to the others. The V-Sync, should I have put V-Sync to one of those and not heatsink? I don't know. Or do I need both to go into the special pins that are, designed to, or they have characteristics that mean that they're ideal to do with clocking? You get tighter clocks if you feed clocks into those, I think, those pins. So the V-Sync isn't on one of those, I don't think. It's just on the normal I/O pin, and that could cause me some issues, is the point. There's no shorts here between any of these, no resistance whatsoever, as you'd imagine, because we haven't got a regulator fitted. Yeah, the point I was going to make though is that this here is not joined to its tab. We couldn't do it here because it would pass through, the connections there. But on the other side, can we do that? Yeah, we could have done, and the reason I didn't do it here is because of the prints. Inspired by Terrible Fire, Live 2, Furtek, Terra Onion, Retro HQ, Mike T, ReSDMac chap, Jay Belander, and importantly Mattias Heinrichs, because I think I'm going to use his code as a starting point for this. And it may well be that we need very little tweaks and changes, and it might be that this is exists because of these people here and the firmware from Mattias Heinrichs, because I suspect I may be able to literally lift and shift his firmware. I just need my pin mappings and things, and it's just whether I've missed anything. The other obvious thing for me, and it might not be the problem I'm thinking, but it's going to be an issue I think that I need to deal with in terms of the final version. And I may help, I may ask if Jay Belander wants to help with this. He might not want to, he might have better things to do, and it might be too difficult, I don't know. But Jay Belander helped Mike T do the ReSDMac, and it's a similar kind of thing with a a similar challenge. In that case there, they used an FPGA and a few other things on the other side as well. So it's quite a packed, dense board, as you'll see in that video. But the point is, Jay Belander is really hot at routing boards, and he might be able to convert this to a 4-layer, more optimally lay it out, put some jumpers on, because I'd like some jumpers to be able to influence functionality, some different functionality that I may add into this. But that's down the line yet. I need to get the basics working first. Things like scan lines. It'd be nice to have a jumper on here. You could just enable or disable and you get scan lines. You can argue, what's the point in scan lines when you scan doubling? But do you know what? You get a really nice representation of the video if you are scan doubling with every other line as just a blank scan line. So you're not really scan doubling, but you are in terms of the output. It's double the resolution, it's double the frequency, etc. But you get the scan line effects, and I tell you what, it looks fantastic with scan lines. I know that because when I tinkered around with the AGA Multifix, which came from Mattias Heinrichs. So I might add some jumpers as the point. This prototype's not going to have that, but I will be able to prototype the code and then leave in place an option for one of what is presently unused. We've got 3 or 4 unused pins around, I/O pins around this. So if those could be additionally routed on the next version to some jumpers somewhere, even if they're solder ones or something somewhere around here. The other thing that Jay Belander might be able to do is, lay this out in a way that allows a PLCC plug to be soldered on the other side. And you might be able to do that now. It may be a case of just designing something where, it comes out on the underside here, and you've got a PLCC thing mounted onto these. I don't know. It might be an adapter, another little PCB that solders on the underside or something. Lots of options and, well, lots of work, and it depends on who wants to help and whether he wants to help or not, and whether he's got more important things to do, and whether this even works when I'm done, and whether I even finish it. It's taken an incredible amount of determination to get to this point, if I'm honest. Yeah, so you can see there's grounds there. So the grounds all look good. I've got ground around this, which is you need on something like this, and I managed to do it just from clever routing of the traces. There are places where there isn't a ground. You can see, like here, there's no ground around there, because you try. I don't think there is. Oh no, there is. There's a ground there. Yeah, it's quite difficult though, because you've got to stitch the ground through yourself, etc. Hopefully I've not joined anything up to the ground. Well, we know we haven't. We've tested ground. Look how close that wire is to that there. Yeah, there are 1 or 2 wires that are very close to things, but anyway, everything seems alright. I'm absolutely amazed that I've managed that. Let me show you the size of the PCB again. And the thing is, you may think, oh, that looks easy, but it's not very big. It's not very big. Can you imagine, look at the CPLD. It's the solder points are going to be pretty hard to do. The way to assemble it, I think, is going to be to get the CPLD on first, and the regulators and stuff and the caps, and then fit the pins around there. And when it comes to the ones next to the CPLD, solder from sort of this angle, like this, all the way around, rather than trying to come in at this angle and smear solder all over the CPLD. But I'm really happy though, because it looks like I haven't balked this initial proto here. But coming back to what I was saying, I ran away with my thought train there. One thing that is a deficiency, other than having some jumpers, is the RGB level of the output. The CPLD is at 3.3 volt levels, isn't it? Yeah. So when it comes to feeding the hybrid, with the red, green, blue signals, they're going to be a wee bit lower than you may expect, and that the hybrid resistor ladder may expect to do the DAC stuff. Your digital to analog conversion there. So we may find that the brightness level is 10% less than it should be or something. That's a deficiency with this, and I'm like, well, when I was designing the proto, I'm like, well, how can I lay that out on here? Well, I could have increased the board in size. Certainly probably would have needed to go to 4-layer, and then route the 12 RGB lines going out to some 245s or LV something, some sort of buffers that translate to 5 volt logic levels. Even that, I'm not 100% sure exactly how I would approach it, because there's a difference on 7.4 series, and this is the thing. So it's not just about getting up to 5 volt levels, it's getting up to the right 5 volt levels. On the 2000, it has HCT chips to do that. HCT. If you put LS chips in there, the logic level's different. even at 5 volt 7.4 series. The logic level is different. So I'd need to get the right buffers, but I mean, where do you fit buffers on here? You can't fit it on this, the way things are. So for the very first proto, I thought, well, let's ignore that. If it's 10%, even 20% less bright as it should be, you can just adjust the brightness on your monitor. Is it really the end of the world for a proto? And then we'll deal with that down the line. And again, there might not be much demand for this. There might be a handful of several people that want one of these and build one. They might not be bothered. I don't know. You know, you connect to a modern display. Are you really bothered about having to adjust the brightness? But it might not just be about the brightness. It might be about the difference. Yeah, it's sometimes, you know, you can increase if your level's down here instead of up here, your top level. Yeah, that means your range of colour, you know, your range of intensity is that wide. When it's down like that, then your range is less. So even if you adjust the brightness on the monitor, well, yeah, will it be the same? I'm not so sure. Blacks, for example, might not be quite as black as they should be, or they might be blacker. It might be blacker than it was before, but then you adjust the brightness, you may artificially pull that lower level up, if you see what I mean. And of course, and the other possibility is to take one of the modern hybrid designs and just modify it to work with the levels that come out of this, and I'm inclined to think that might be the easiest route. Yeah, use a modified DAC that goes with this, pair the two together effectively. So yeah, that might be the way I go. Which brings us to the end of the first part. Now, I realise this is a much shorter episode than normal, so the next part will follow very quickly after this one. For my patrons and YouTube members, it'll go up literally today, same day. But I'm breaking it up this way into more manageable chunks, and you can just watch the bits that are relevant to you. So, you know, in this first video here, we just covered the, you know, the premise, what it's about, what it does, and the first look at the first revision PCB. In the next video, we're going to build that up, and we'll start working on the code side of things and doing some testing and working through some revisions. I do hope you found that video interesting. If you'd like to support the channel, please see the Ko-fi and Patreon links down below. I'll catch you in the next video.